Hey my lovely level 3s and welcome back to 3.4 Atomic Structure and Bonding, and this is lesson 8 part B, and our learning objective is to learn about the octet expansion and what that means. So I guess here's a Lewis structure that you can see at level 3, and how is this different to what we've been doing? Hopefully straight away the biggest thing that you are seeing is the fact that instead of having phosphorus having 8 electrons around it, you can see that there are in fact 10. So this means that phosphorus can't be obeying the octet rule, and so something else has to be going on, and that's what we're going to be introducing today. So there are actually exceptions to that octet rule that you already knew. So you already knew that hydrogen needed 2 electrons, beryllium could have 4 or 6, and boron could have 6. You may not have been as familiar with the beryllium one because it doesn't come up all that often, but you definitely would have known hydrogen and boron. So what octet expansion, what is this? So for atoms with an atomic number greater than 14, particularly phosphorus, sulfur, and xenon, these atoms can undergo octet expansion, which means instead of having just 8 electrons around them, they have 10 or 12 electrons with 5 or 6 bonding regions. Now this is quite unusual. Now why it happens, we actually don't need to know why it happens. I do generally teach this in the classroom and your SciPad has pages on this, but we're actually not going to worry about that now, and I'm not going to get you to do those SciPad pages. If you really want to do them, you can, but what is happening is that electrons are promoted to a vacant d orbital, and if you do scholarship, we'll do it. So let's have a look at PCl5. PCl5 has got 40 electrons, okay, giving it 1, 2, 3, 4, 5 electron density regions, and phosphorus has got 10 electrons around it. And here's PCl6 minus, 48 electrons, and 1, 2, 3, 4, 5, 6 electron density regions. Just a reminder that if you do an ion, they're drawn in square brackets and the charge goes outside. Okay, so we've got 5 electron density regions and 6 electron density regions, and these are our new parent geometries this year, which is pretty exciting. So how do we do these Lewis structures compared to Lewis structures of 8 octets? This is just reminding you of square brackets, folks. So square brackets, charge outside. So it's actually the same as always, except for octet expansion. So you do count the valence electrons, work out the central atom. This time, place your 5 or 6 surrounding atoms around that central atom, plug in the electrons, and then if you have any extra, place them on the central atom. This will make more sense when we've done a few examples, and I'm just going to spend most of this video doing examples with you to make sure this is all sinking in. Excuse me, there are 6 examples here, and so we're going to complete these Lewis structures. So the first one we're going to do is this one here. So we need to add the electrons. So you really do need to know your group numbers or know how to use your periodic table. So group 14, so 4 valence electrons. Group 17, and so that, but there are 6 of them, and then you need to add 2 because it's a 2 minus, which means it's gained 2 electrons. So if you add that all together, you end up with 48 electrons. Now silicon will be the central atom because it's by itself, and I'll have to move around the page here and it won't be the neatest, but who cares, we'll figure it out. So what I'm going to do is I'm just going to, I know that there are 6 surrounding atoms, so I'm just going to make 6 little zones and put 12 electrons around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then I'm going to put in my Fs on each of these zones. And now I'm going to add in the rest of the electrons. So I've used 12 electrons, so 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Huzzah! They've all got enough electrons. Silicon has got 12, and all of the fluorines have 8, and that is the Lewis structure for SiF6 2 minus. The one thing we've got to do is, because it's an ion, square brackets with the charge outside. So hopefully that made sense. We're going to do BrF3 now. group 17, 7 electrons, group 17, 7 electrons. So all of that adds to 28 electrons. Central atom is going to be bromine. This time you've only got 3 surrounding atoms, bit of a different one here. So we're going to do those, put the 3 atoms around. So 1, 2, 3, 4, 5, 6. Chuck the fluorines, apologies, around there. Okay, so we've used 6. Okay, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So we just put the extra ones on that central atom. So what you'll actually see is that you've got 1, 2, 3, 4, 5 electron density regions, which is pretty cool. So you just put them on according to how many atoms and then chuck on the extra electrons on that central atom. Let's do PCl6. So phosphorus is in group 15, chlorine's in group 17, and there are 6 of them. So when we add this all together, you get 48 electrons. Now you should start to see, if you get 6 atoms and 48 electrons, it looks like this, okay? Because 6 8s are 48. And so you get familiar with the numbers and kind of how it's going to look. So phosphorus in this example will be in the middle, and we're going to do 1, 2, and I'm just going to chuck on my chlorines as I go. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Huzzah! So it all worked. Square brackets and then a negative charge because it's an ion. So hopefully that makes sense. We're going to jump and do SF4 up here. So SF4, okay, this one here is group 16 and F is in group 17. So when we add up these electrons, we end up with 34 electrons, and S is going to be in the middle. So we've got S, and we're going to put the 4 fluorines around. So 1, 2, 3, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And what you'll see is we're getting there, 27, 28, 29, 30, 31, 32. And then we've got 1 spare pair, so we just chuck them on. And so this one has got 1, 2, 3, 4, 5 electron density regions. Okay, so octet expansion. Perfect. So now we'll do NF3. Okay, it's really important that you just see a bunch of these examples, which is why I'm spending a bit of time on this. Group 15, 5 electrons, that's group 17, times 3. So when you add that together, you get a total of 26 electrons. N in the middle. Okay, I'll put my 3 fluorines around. 1, 2, 3, 4, 5, 6. 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, so this one here hasn't gone past octet expansion, which is totally okay. So that one would just be a trigonal pyramid. Okay, so the next one we're going to do is IF3. Okay, and all of these are group 17, and so they add up to 28 electrons. Okay, so I 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we've used 24 electrons, 25, 26, 27, 28. So hopefully that makes sense, and you can see 1, 2, 3, 4, 5 electron density regions. So hopefully that makes sense. You're going to do a bunch of practice later today. And here's all the answers. It's just what we did there. Okay, team. So there's one last section before the end of this lesson, and what if there are only 4 surrounding atoms, okay, and they ask you to do octet expansion? And so if that's the case, you force octet expansion by creating a multiple bond. And so we're going to do this now. So if we add up the electrons of this one, we get 32 electrons. This is the valence electrons. This one you get 32 electrons, and this one you get 32 electrons, just to save a bit of time. So I'm going to do P04 over here. So P is the central atom. It's got 4 O's. So 1, 2, 3, 4, 5, 6, 7, 8, 2. Okay, so 32 electrons. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So you're probably thinking, well, what the heck, Miss Sutton? It's sweet as, it's got 8 electrons. So if this was ever a case, you're not going to see this sort of question in your exam. This is kind of pushing things. But if you wanted this to have octet expansion, all you would do is move a pair of electrons and create a multiple bond. Oop. So this, because you can see here I've moved these electrons, well, if it'll let me bloomin' do it, it's not letting my pen go. There we go. You can see now the phosphorus has actually now got 10 electrons around it instead of 8, and the oxygen's still got 8 electrons. So you can just create a multiple bond in order to give that central atom more electrons. Now, why on earth would this happen? This is actually beyond kind of level 3, and if we were in the classroom, I'd teach you this. This is called formal charge, and you need it for scholarship. So scholarship kids, I'll run through this with you. Otherwise, all I'm wanting just level 3 kids to understand is that you can actually force octet expansion to happen by creating a multiple bond, and this does actually happen because some molecules gain stability by having several multiple bonds in them. So we'll do one more before my video runs out of time. So let's just do SO42 minus. So S 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 23, 24, 25, 26, 27, 28, and 32, and you can see it's satisfied, but we can actually move a pair to create a multiple bond, and all of these should be in square brackets. There should be square brackets. So hopefully that makes sense. It's not likely you're going to see a question like this, but I just wanted to expose you to the fact that even though sometimes when you don't think that you need to do octet expansion, those structures can actually be more stable, but there's a whole other section called formal charge that needs to be taught, and we're just sticking to the basics in these videos. Scholarship kiddies, you will learn that with me. Cool, so we have actually finished lower structures, and next lesson I'll see you for shapes, which is awesome. Okay, see you team.